Welcome to Microsoft Campus Tours. Today we are in Studio B and we're going to check out the Surface 2.0 hardware test lab and meet Patty, the test robot that stress tests all of the new Surface 2.0 hardware. Let's go. All right, we are here with Joe, who is the operator and looks after Patty, the Surface 2.0 stress test robot. Hi, Joe.
Yeah. Hi. Nice
thanks for your time. So we're really interested in Patty. Tell us, what is Patty? How does Patty work? This is amazing.
Okay, so Patty is a stress test robot, and the idea is instead of having a bunch of monkeys sit there and pound on our Surface 2.0 all day, we had a robot built for us that will help automate that. So the way she works is we need something to actually go down and touch the Surface unit. So we've got we'll call these probes here. And when this is flat down, it presses against here, and we can see the contacts coming down. We've got a couple different types here. We've got what we refer to as a blob. This is just a contact that has no necessary shape or value on it. We've got some here that are tags. This is what you put on the bottom of an object. And then we've got one here that looks like an infrared finger. It's shaped to look like the infrared image of a finger to the surface. So I can put that down and say, okay, did I see a finger go down and stuff? And this has 6 motors. It has an XY, so here's an X position here. Also, this part moves forward and back, so it's the Y position. And then each of these is a motor behind it that will control for rotation. And Patty's the second series of a robot, which we used to call PD. P used to have 1 probe that would go down. Patty has about 80 of them. And what we can do with these is put down more than one at once and then do gestures like stretches and zooms. So this gives us a very nice, easy way to do multi-touch runs for, let's say, a week and simulate what we'll have out in the wild when our Surface 2.0 is out in public.
Cool. And how do you have each of the individual probes kind of moving forward and backward to simulate the touching of fingers? How does that work?
So what we do is the motors are all electrical. The probes are all air-driven. So what I'm going to do is I'll cross over here. And this is the Profibus portion. And when you hit here, air passes through and puts the probe down, basically.
So you've got compressed air coming into the building somewhere.
Yep.
And it's running into a series of tubes.
Yep. Yeah, basically it's a series of tubes.
And I just wanted to say series of tubes.
Yeah.
and triggering each of these, are they just their valves, are they? Or what are you actually
exactly.
doing?
So there's valves just on each of the side that control about 30 or so of the probes each.
Okay.
And yeah, we can basically turn them on or off binary and say, put a probe down. Now, it doesn't give us pressure, but it does give us a binary, I want a finger down or up right now.
And you could have all 80 on at once if you wanted to?
Yes, absolutely.
Wow. Absolutely. So if there's a whole army of school children playing with the Surface all at once, you can actually emulate that.
And that's the kind of things we want to simulate. If an army of school children wants to play on it for 24 hours at a time, we want to make sure that we can stand up to that.
Awesome. Now, you said this kind of moves in an XY axis. We'll see it moving hopefully in a few minutes.
Yep.
But kind of tell us how that works and how the robot knows where it is and moves around.
Sure. So there's a National Instruments controller card that we'll go take a look at, and it's going to actually turn motors on the back here, which turn these belts, which actually drag this on both ways, and then also are plugged into here. So what we'll do next is we'll take a look at the box that has all the motor controller components in it.
Cool.
Okay, so this is the control panel for the National Instruments cards, basically, that control the motors, the 4 motors. We've got the X, Y axes and the 4 rotations. So that's 6 motors total, so each one of these is a motor controller here. And this gets passed through to what you see, the red and the white switches over there with the red lights on them. Those are called limit switches, and they have sensors on the unit. When the sensor is covered, it tells the robot, hey, you're all the way over on your x-axis, or your center, what we call home on the x-axis. And what we do with these limit switches, that'll actually cut power to the motor if they're activated, if we cross over them. So that's a safety design there. And then below that, you'll see the 2 National Instruments cards that control the motors. Each one is able to control up to 4 motors. And so since we have 6, you'll see 4 on the left on the blue card there. And then on the right, you'll see 2 of them used with 2 open that we're not using currently. That card runs into this PC here, and this PC actually controls the software that runs the entire robot. You'll also see this pink wire here that goes to the head of the robot. This controls the air system. And basically, all of those electronics are on the head. This is for the probes going in and out. And that's pretty much this unit. Everything else is fuses and electrical that I honestly don't understand myself. So that's this. And then if you want, we can go to the software and show you what the APIs look like and actually show the robot in motion.
Let's do it.
Okay. Okay, so the next thing we want to talk about was the code part of it, and how simple it is actually to control the robot. When the robot was handed to us, it's, like I said, 2 separate systems. We had a National Instruments for the motors, and then we had the Profibus protocol for the air. So we had 2 totally separate systems that we wanted to control, and we had to talk to them separately. So we designed a static class around what we call the head unit, which is the part that has the spinning parts and the XY axes. And I made a static class that has, I'm going to go to the code here. And off of head unit, we made methods move to center, move to point on screen. And I can simply pass in point on screen here. And that call there will actually move the head unit to that point. Now, there's some math involved in this, in that the probe, the center probe will be over that point, but the probes on the outside will not. So I have to actually do some offset math to say where a probe will actually go down on XY. The next part of this is to actually set the probe down. We have what I call the probe grid is another static class. And we have methods off of this, all probes up, all probes down, random probe down for stress. Or I can just say I want to place a single probe down. And what we have is basically it takes a byte for which ID of the probe that we want to place down. So if I say 10 here, which is a probe in the upper left-hand portion, these 2 lines of code will move the head of the unit to pixel coordinate 1200, 300, and then I'll place a probe down. I can call probe grid all probes up to get that probe back up before I make another move to make sure that we're safe, and then go place it to another point. So it's very quick and efficient to do any kind of automation with this the way we have it. So what we're going to do now is we'll make the robot move, and I'm going to show 2 short stress demos. This test here is moving to random points and then placing the basically a tag object down 5 times. This would simulate a bunch of kids basically throwing toys on the table. This next sample is going to be drawing an X basically on the screen. This is something we do on our attract animation at the beginning of Surface to simulate running contacts through the simulated water that shows up when you first walk up to a Surface unit.
Stress sample complete. Testing complete.
Those were samples. We could run that over and over all night long, come in the next day and analyze data, look for debug dumps or crash data, and see if the product was stable. Okay, so now that we've run the test, we want to see the test data and see what shows up. So what I have on the screen here, remember the application over there has an HTTP server on it, so I can browse to it. And I can see the test data that comes back. So I can see that I've got 68 blobs that have gone down in this test run. And I can see stuff like their locations, how many I've put down per second. I can also see things like CPU usage and memory to see if we're leaking it if I run it overnight. So this spit out of data here is constantly running. If I refresh it, I'll get new data for whatever's on the panel right now. And I can run this during the test to make sure, as sanity check, to make sure I'm not doing anything crazy. Or you can just run it afterwards and get a feel for did we pass or fail the test, or are we leaking memory on a stress case overnight.
Awesome. Well, Joey, thank you very much for showing Paddy. Very, very exciting. I think a lot of people who have known of Surface and seen Surface demos and played with the unit probably didn't realize the amount of incredible testing that goes into creating a product like this.
No, thank you.
So I wanted to ask you, though, what's with the gate?
Oh, yes, the gate.
Are there puppy dogs that kind of run around here that need to be...
Wouldn't even hold a puppy dog in. No, the gate's a safety mechanism.
Okay.
And it's actually, I don't know if I should call it advanced, but it does have a magnetic lock on here. So if we open the gate, it'll actually, when this magnetic lock opens, it actually cuts power to the motors.
Okay.
The thing about this unit and its size is it's got to be very powerful to match up with our user research data. Our user research data says that a hand motion across the screen at about 25 inches per second is naturally a good tracking speed.
That's very fast, though, isn't it? 25 inches a second?
It's extremely fast, and it's a speed that we want to be able to simulate. That way we can do some kind of perf testing or see, like, can we respond to those contacts. Now, to do that, you've got to have giant motors to make that giant head move that fast. Now, the head we think weighs about 150 pounds, and if it's moving at 25 inches per second and somebody were in there to get hurt, it would be damaging. So they required this gate with its safety mechanisms, and we've got like the red stop buttons, basically as a way to kill the power to the unit. Now, one interesting story about this is before we had the gate, when we were building the unit, the limit switches I talked about that kill the motor, well, they hadn't tested those yet. So the first test of those were actually reversed.
Oh, no.
What that caused is the head of the unit thought that it was off to the end. And the way the robot works is it throws full power to the motors to correct itself. So when it thinks it's in the wrong spot, it threw full power to the motors and tried to go to the center. Well, that actually moved it all the way to the edge. There was no limit switch to stop it, so it actually hit. And this entire table that it's built upon, the head unit, everything moved. So what this required next was actually to have us bolt it into the concrete of the floor.
That sounds awesome, by the way. I want to see the whole thing lurch across the room and like walk like an AT-AT.
It's scary.
Awesome.
It's scary, especially if you're alone at night and you're testing on it and you do something wrong and it moves. It's scary. So having it bolted, having the fence, seems a little bit obnoxious, but it's actually a really nice safety mechanism.
So safety mechanism is the gate with the magnetic lock, and you have the wonderfully awesome emergency stop button here next to you.
Yes,
with a big just
right there.
Bang.
And it lights up, which is the best part.
That's awesome. Well, Joe, you have a cool job. Thank you very much for showing us, Paddy, and we look forward to seeing Surface 2.0.
Thank you so
Awesome.
much, guys.
Thank you.